that's enough for this one. Next time, we're going to be importing the rest of the molecules that we need to actually create the DNA and stitching them together. So it won't be as long between this tutorial and the next one, I hope. So it's been quite a long time since part one. Sorry about that. It's been quite a lot going on in my actual academic life in the past year. But finally I've gotten around to completing the tutorial and actually building our DNA molecule. Now part one was mostly about writing the code that's designed to import molecules using JSON files into Blender. So if you're interested in doing that, you can go back and watch part one. But if all you want to do is build the DNA molecule, then you can start right here. There's no need to do the stuff in part one. That's just about the import code. So to get started, you want to open a new Blender project, and then in the window, press A to select everything in the scene and delete it. So we're starting with a clean project. And then what we're going to do is import the molecules that make up DNA using the scripting window. So before we do anything else, we need to actually get the scripts that are going to import these molecules. You can either do that by following the steps in part one to take strings representing those molecules in Smiles notation, and then compile them using Python and turn them into 3D objects, or you can take a shortcut here and you can go to the GitHub repository which I set up, which is in the description of the last video, and you can just download the scripts from here. Oh, sorry, in this window. Okay, so I've just unpacked this, and here I have all of the scripts from last time. So here we've got the JSON files for adenine, cytosine, guanine, and thymine, which are the base pairs, and the deoxyribose backbone for DNA. We have the Python code that allows you to convert between Smiles notation and the JSON file, and then we've got the molecule builder code that actually turns this into a 3D object. And this is the thing that we're going to need to actually put in the scripting window. So go ahead and open up this text document. And here is the code that we developed last time. So we're just going to take all of that code, Control-A, Control-C, and then we're just going to create a new script in the scripting window and then import that. And there we go. So if we go into the folder we downloaded from GitHub, we can see that we've got JSON files of each of these molecules. Okay, so each of these names just goes into this line here, and then the script will build that into a 3D molecule. So what we want to do is for each molecule that we're importing, we want to put this into a new collection. Okay, so let's just start at the top of the list with adenine. So if I just put adenine in there, and then I need to make sure the file path is correct. So if I go back to my folder, I can just copy and paste that file path. Okay, so let's just run that. And there we are. Here's our molecule. Okay, so you'll see here that this is made up of all of these individual cylinders and spheres. So there's a lot of different physical objects making this up. And if we had to try to deal with each of these independently and move them all one by one, that would be an enormous pain. We definitely don't want to do that. So instead, we're going to treat all of these objects as a single collection. Okay, so if we click this arrow, we can collapse this collection, and then we're just going to rename the collection. If I can find the naming, there we go. We're just going to rename this adenine. Okay, and this will just help us to keep track of what we've got in here. All right, okay, so oops. Click on Scene Collection and then click New Collection to make a new one in this level of the hierarchy. And then we'll just continue to do this for each one of these molecules. Okay, so I'll speed this up so you don't have to watch each one in laborious detail. Okay, so now we have all of the molecules that we need to make up DNA. They're all smushed on top of each other, but we can isolate the ones that we're interested in just by ticking these boxes, and that will prevent them from being loaded into the scene. So, for example, here's the deoxyribose molecules. So these chain together to form the backbone of DNA, and then the actual base pairs anchor onto this pentagonal ring here. By the way, I'm a physicist, not a biologist or a chemist, so sorry if I use all the wrong terminology or use rubbish words to refer to things. Okay, so when we loaded this molecule in, as well as importing the geometry, we also created materials for everything. So you can see if I click on these atoms in the materials tab, here I have phosphorus on this, here I have oxygen, here I have carbon. So we want to set the molecules, the atoms rather, to be the right kind of color for the final product. We don't just want everything to be gray. So let's just run through all the materials that we've got and set these up. So carbon usually is depicted as being kind of shiny black. So for that we can just click on base color and make that black. And we can increase the metallic. If you want a preview of it, click the drop down preview here and you can see a sphere that's rendered with the right material. So that's fine for carbon. This is oxygen. Usually I see oxygen depicted as red, so we can make that red. Hydrogen is often depicted as kind of white metallic, so let's make it white and crank up the metal there. And then what's this? That's phosphorus. Usually that's kind of yellowy orange, so we'll put it as yellowy orange. And the actual bonds, well, they can stay just white. That works in a ball and stick model. Okay, and what I'm going to do now, I'm just going to go back and check. Yeah, so there's some atoms that we haven't colored yet. Nitrogen, that's usually blue. There we go. Any others? I think that's all. Yeah, so everything's now got a material attached to it. So there's none of the atoms that are just grey. Okay, so at this point, I just want to outline something. So one of the reasons why it took me ages to get around to recording this second session is because when I went and looked up other people who've done Blender tutorials on building molecules, I found that a lot of them were a lot better. In particular, there's some that allow you to import directly from CIF files or import directly from Avogadro, which is a molecule building program, including importing full working models of DNA. So I'm going to link some of those in the description. I'm not trying to monetize this in any way, so it's no skin off my nose if you prefer those tutorials. The difference with what I'm doing here is that we're building the DNA molecule by molecule as a teaching exercise so that you can learn a bit more about how Blender works. But also I would say that this method is useful if you want to build DNA with a custom sequence. So rather than importing in a model that already has the base pair sequence prearranged, here you can build it custom. It's not much of an advantage, but it's something. But yeah, if you want to just learn a bit about how to use Blender in a sample project, this is what this is intended for. It's not supposed to be the optimum way of building DNA. Okay, so with that out the way, what we now have to do, now that we have all these collections with the individual molecules in, we need to actually pair up our base pairs. And for this, it's useful to get a reference up, especially if you're a dumb physicist like me, so that you know which base goes with which. So we need to pair up thymine and adenine and cytosine and guanine. So we're not going to do that just by grabbing these collections and moving them around. These are going to act as our kind of originals. So we're actually just going to copy the relevant collections. Okay, so let's load up thymine, and then if we right click on here, we can duplicate the collection. So let's do that. And then you see now we have thymine 0.001, so that's our copy of it. And then we want to do the same with adenine. So let's untick that, highlight it, right click, duplicate collection. Now we have adenine 000. And we can just move these down to the bottom, hide that one. Okay, so if we, when we're looking in the viewport normally, we're looking in perspective mode where we have full 3D perspective. But often when you're actually trying to align things, this is not particularly helpful. So you can use the numpad to get an orthographic perspective. So for example, if I press 7, then I go to top-down orthographic perspective, 1, a side view, 3, the side view at 90 degrees, 9, 90 degrees the other way, and then you can press the 4, 8, 6, and 2 keys to get 45 degree position. So this allows you to just view without the distortion of perspective for the purposes of lining things up. But we want to go press 7 so that we're looking at it top down. And then our goal is to line these up so that they look like they do in the reference image here. Okay, so let's start with thymine first. So we'll highlight this collection, and now if we press A, we select everything in the collection. So the way that this should be lined up is we should have this edge here, the oxygen, nitrogen, oxygen triplet here, that should be aligned to the edge of the adenine. So that means that this nitrogen atom here is going to be the center of our molecule. So if we press Shift and click this nitrogen atom, you'll see it's now highlighted in yellow rather than orange. That means it's the active object. All of these are still selected, but this is the active object. So if we do anything now that affects material properties, it will be applied to this as the center. Okay, and what we want to do now is pair all of these objects to this. So what will end up happening is in the hierarchy, all of the other objects will end up being children of this object. And the way that we do that is by pressing Control P. So set parent object to and press object. And now there are all these dotted lines that show these links. And now if I just highlight this nitrogen atom and I press G to move, and I move around, you can see the whole molecule moves with that atom. Okay, so now we can just go to the N menu up here, this pull-out menu at the top, which you can access also by pressing N, and we can set this location to 0, 0, 0. Okay, and now it is on the origin. Press full stop to zoom in on it on the numpad, so it's in the center of our view. Okay, and now we need to rotate this so that these 3 atoms are along the y-axis. So for that we press R to rotate, and then Z, so we're rotating around the Z-axis, and now we can just rotate it, and there we go. That is now correctly aligned. Okay, so that's thymine done, and thymine pairs with adenine, so let's bring that one up. And in this case, the relevant alignment is along these 2 nitrogen atoms here. Okay, so we're going to do the same thing, press A to select everything, after deactivating the thymine, of course, so that that's not loaded into the scene. Shift click on this nitrogen atom, which will be our center, Control P, make that the parent, just as before. Use the N menu to reset the position to 0. Press RZ to rotate around the Z-axis and rotate it until it's aligned. If you need to do finer rotation, you can hold Shift while you're rotating and it will do a finer rotation, or if you want coarser rotation, you can press Control. Oops. Okay, there we go. That is now lined up. Now, of course, if I load these in on top of each other, these 2 nitrogen atoms sit on top of each other, which is not actually what we want. We want them to be separated in space. And actually, if we look here, we can see that some of these hydrogens are in different places in the actual pairing as opposed to the molecules that we've loaded. And this is a problem that we're going to have to solve in a couple of cases, because when we imported these from Smiles notation, we imported these molecules as they exist in isolation. So a lot of them have terminating hydrogen atoms where they shouldn't actually be, or hydrogens that are in different positions, and with the deoxyribose as well, there's a couple of terminating hydrogens which actually shouldn't be there. So we're going to have to edit these molecules a little bit to get them into the state that they should be in DNA, but they're otherwise geometrically accurate. Okay, so we're going to separate these a little bit in space. Now, normally what we've been doing so far is in the N menu, we just type positions in here and then it moves, but you can also actually drag in here and then you can see the exact position that you're moving to. So what we want this nitrogen atom to be offset from the y-axis by the length of one hydrogen bond, so the length of one of these cylinders. And for now, we can just make that approximate. It doesn't need to be perfect. So that will do. And then the other one, we want it to be offset by exactly the same amount. So, oh, whoops, rather the opposite, -1. So there we go. Let's update that to 1 just to be a round number. Okay, and now in order to match this diagram, we just need to get a hydrogen bond moved to this nitrogen atom. And in fact, we can do that with the existing models, because these two terminating hydrogens actually shouldn't be there when these two molecules are bonded in DNA. So one of them, we can just highlight the individual models and delete, but the other one, we're going to actually move it. Okay, so shift-click both the ball and the stick, and what we now need to do is unparent it from this nitrogen atom, because all of its positions currently are relative to this. So when we unpair it, it'll move off to some crazy position. And the way we unparent is by pressing Alt-P. Okay, so this clears parent information, and we want to clear the parent, but we want to keep its position in space. So click this one, and now you'll see it is a separate object. It's no longer paired to this. Okay, so what we want to do now is we want to move this so that the bond is in the center of this nitrogen atom. So in order to make that happen, we're going to parent this sphere to this cylinder. So Control P, set parent object to the cylinder. So now these are joined together again. And if we zoom in on this object by pressing full stop on the numpad, you'll see that these yellow dots here, these represent the origins of the meshes. And currently they're in the middle, which is not very helpful, because if I want to move this down to this nitrogen atom, I'll have to kind of position the end manually. So really I want the origin of this object to be the end of this cylinder. But fortunately we can do that relatively easily. So when you're looking at the, when you're in the viewfinder, press Alt-Z to go into X-ray mode. So now we can see through all the surfaces. And then press Tab to go into edit mode. So now we can see the mesh. And if we go up here, if you remember, these three icons determine what you're selecting in the mesh. So currently we're selecting vertices, which are the yellow dots. If we press this, then we're selecting the lines of the mesh. And if we press this one, we're selecting the faces of the mesh. So use this and select the end of the cylinder. And now, if you're in edit mode and you press Shift S, you'll get this cursor menu that allows you to move the cursor to specific places. And it includes both the actual mouse cursor, the screen cursor, but also the 3D cursor, which we haven't really used very much. The 3D cursor defines a point in space rather than a point on the screen. So move the 3D cursor to selection, which is the end face, and you'll see now this sort of dotted circle, this is now on the end face. And now what we can do is if we right-click, if we press Tab to go back into object mode, and then we right-click, we can set origin to 3D cursor. Now you can see both this sphere and this cylinder, their origin is this end face. So now if I press Alt-Z to get out of X-ray mode, press 7 to go back into the top-down orthographic view, now I can move this object by going into the end menu and typing in 0, and this will move to the origin. If I put -1 in X, this bond is directly centered on the nitrogen atom, and now all I need to do is press R, Z, and rotate it so that it is completely horizontal. And there we go. Now this hydrogen atom is sitting in the very center, which matches up to what we want for the adenine thymine pair. Okay, and before we move on, we can just check for any other errant bonds that shouldn't be here. I think this this hydrogen here on the nitrogen shouldn't be there, so we can delete that, and then that is fine. Okay, so now we've got our adenine and thymine pair, and we've got them arranged correctly in space, but we don't really want these to be separate objects, we want them to be the same object. So while they're both loaded into the scene with the tick, press A to select all, and then we want to apply all the transformations that we've made. So this is an important point to note about these transformations in the end menu. What's really happening here is it's like when the object is being loaded into the scene, it's being loaded at the origin, and then it's applying this transformation, so a motion in X and a rotation in Z, in order to get it where we want it. But what that means is that if we then apply further transformations, we're adding all of that on top of the existing transformations. And sometimes, depending on what kind of coordinate system you're in, that can produce some really weird results. So we want to change this so that rather than these transformations being applied from the origin, these meshes are in the correct positions, but all of their origins are at 0. So the way to do that is select everything here with with just pressing A, and then press Control A to get the Apply menu, and here we can apply different transformations. We want to apply all transforms, so that will mean every single mesh now has its origin back to 0 and has just zeros in this transform drop-down menu. Control A, all transforms. There we go. So now you can see this yellow point, which denotes the origin, is centered on 0, 0, 0. And all of these are still parented though to other things, so now we need to get rid of the parenting. So press Alt-P and click Clear Parent. It doesn't matter about the transformation now because we've already done all of that by applying it. So if we look now in the hierarchy, we can see there's no parenting now. All of these objects are at the same level in the hierarchy. But it would be useful to parent them to the very center, this central hydrogen atom, so we can highlight that with Shift click and then Control P, set parent to object. And now, of course, if I click this central hydrogen atom and I want to rotate, the whole molecule rotates around it, or the whole molecule moves around it. Okay, so this is now our adenine-thymine base pair. And again, even though we have these in separate hierarchies, it's good to keep the original intact if you do other things. So what I'm going to do is press Control A and then copy all of these meshes, go to the scene collection, create a new collection and call it A-P for the adenine-thymine pair, and then copy all of those meshes into this AT collection, and then I can deactivate both of these. Okay, so now this is in a single collection, which is much more useful for what's going to come next. Okay, so now we've done this with adenine and thymine. Now we need to do it with guanine and cytosine. And again, I'm going to just speed up this process because it's exactly the same as what I just showed you, except with slightly different molecules and geometry. You know, I'm sure you'll be able to figure this out. If not, then you can just watch at a slower speed as I work through. Okay, right, so let's go. Okay, right, there we go. So now we've got both pairs. Now something that's going to be really important later is that these rings line up. So they're not perfectly lined up right now because you know, we've done slightly different rotations while we were trying to line everything up. So we just need to rotate both of these to make sure that specifically this nitrogen atom here lines up in both cases and this one. Okay, so to do that, I'm just going to select a central hydrogen atom. This is in the CG pair, and I'm going to hit RZ, and then I'm going to just rotate it until it lines up, or as close as I can reasonably get it. Okay, so it's not quite perfect. You can see there's a line here where the meshes don't perfectly match up, but it's very close. Okay, so what that will mean is that when we then build the deoxyribose backbone, and we have the bond here that's supposed to bond to the two pairs, it will bond to both in the same position. Okay, right, so now that you've got them aligned, it's time to build the deoxyribose backbone that's going to attach to these. So if we bring in the deoxyribose molecule, we can see that it's in no way in the right position or orientation. And we're going to use this trick again of using the end of a bond to guide where we're going to place this molecule, but on a much bigger scale. So let's hide the 18CG and have a look at this deoxyribose. So this is not actually quite as the molecule will appear when it's in the chain. So it bonds together in a chain on this oxygen here and this oxygen here. So only one of these is actually present when it's in the chain. And then it bonds to the nitrogen atom in the base pair where this oxygen is. So these OH groups here, they're present when the deoxyribose sugar is isolated, but we need to get rid of them. So first of all, let's just delete all of these unnecessary bonds. There we go. So now chemically this is correct, but geometrically it's still not quite right. So first things first, we need to parent the whole collection to this bond. So press A to select all, shift click on the relevant bond, Control P, and create that parent relationship. And now we want to do this thing where we put the point of origin at the tip of this. We're going to do this a lot while we're arranging this molecule. So as a shorthand, I'm going to refer to this as end snapping. Okay, so press Tab to go into the mesh, select the face on the end, Shift S, put the 3D cursor on the tip of the bond, Tab to go back into object mode, right click, set origin to 3D cursor. And now everything moves relative to that bond end. Okay, so now we can bring in one of the pairs. We only need to do this with one of them. So we can start with the AT, and let's go into a top-down orthographic mode. Okay, so we want to bond to this nitrogen atom here, but if we click on this, we can see in the transform everything is 0. That's because we applied all of the transforms, so the actual origin of this mesh is this point in the middle here. But we can reverse that just by right-clicking on the atom, and then clicking origin to geometry, and now it's recovered all of that original information about the location of this atom. So now we can copy and paste this information into the end bond that we were looking at before, and then that will move the deoxyribose sugar into the right position. Now, unfortunately, for some reason, you can't copy all three components at once. You have to do them one at a time, which is a bit annoying. It doesn't take too long, just copying and pasting this information in. There we go. So now this is bonded, if you like, to the right position. But if we bring up our reference image here, here we can see that if we look in the top-down view, this is clearly not quite right. It's about 90 degrees rotated off where it should be. And actually, if you look closely, even if we rotated this to where it should be, this oxygen is on the wrong side. Okay, and this is, I'm not exactly sure why this is mirrored in this version, it just is, but we can fix this relatively quickly. So first of all, we need to rotate this molecule so that it's in the right orientation. So we're rotating it through 90 degrees. So I'm going to, with this bond selected, press R, and I'm rotating it in X. So I then press X to rotate it solely around the X axis, and then hold Control, and that will allow me to rotate in increments of exactly 5 degrees. And I'm going to rotate that so that the number in the top left there says 90. Just realized my screencast keys aren't working. There we go. Okay, clearly this is still not quite right, but that's because it's still inverted with respect to where it should be. So let's deselect that AT molecule for now. A to select all, Control A to apply all transforms. And now we can flip this in Z. If we tried to flip this before, then we'd get different effects being applied to different objects depending on their relative positions, but now they all have the same origin. So if I put -1 in the Z scale there we go, it's mirrored. Okay, so this is still not quite right. We can see the orientation here isn't perfect. So if I bring the AT back, and then we want to do this end snapping on this bond again to make sure that we're only rotating around the bond end and not around any other reference point. There we go. Alt Z, by the way, that's just to go into X-ray mode. Okay, so I'm going to rotate this until that bond is approximately flat on that surface. and have a look. Maybe not quite. There we go. That's a bit better. And now it needs to be rotated in this axis, so RY. And there we go. That's much closer now. Maybe a little more, actually. There. Now, this is obviously not perfectly accurate. I'm not reading these angles off of anything to get them exactly right. But we're going to make sure that these chains all link up in a moment. Okay, so next thing, if we are to... if we zoom in on part of this model, we can see that actually this chain of carbon atoms should go like this. So we have 2 up and then this one goes down. Whereas here, this phosphorus is actually in the wrong place. It's on the wrong side. And again, this is just a thing about the mirroring of the molecule from the Smiles notation that we got. I'm not entirely sure why it's loaded this way, but it has. But again, we can fix this relatively quickly just by mirroring this component of the molecule. So let's just quickly hide that AT so we don't accidentally select it. Press Alt-Z to go into X-ray mode, and then just drag a box around this relevant area. And now we want this bond here to be the parent. So forgot to apply my transforms. Let's make that the parent. Okay, it's not wanting to do it. Let's try selecting all and apply transform, and then redo that selection. Okay, that's better. And I want to end snap because I want to rotate around the end of this bond. So go into the mesh, X-ray mode, select the end, Shift S, 3D cursor to the end point, press Tab to go back into object mode, right click, set origin to 3D cursor. That's great. Go back out of X-ray mode, and now let's mirror this in Z by putting -1 into the Z box. Good, that's a bit too much though, so let's press RX and rotate that back to something a little bit closer to how it appears in the other model. And actually as well, this needs to be rotated a bit in Y. And then if we go and we look at how it appears here, this phosphorus should actually be rotated in this direction. So again, press A to select all, Control A, apply all transforms. And then let's just select around this oxygen atom here. And this time we don't need to end snap, we can just make the center of this sphere the origin, and then rotate around Z. And we can rotate around the local Z by double pressing, local Z? Okay, that's strange. There we go, we can rotate around local Y, that will work, by double pressing the key that you want. So if I press RY, then that's rotating around the global Y-axis. If I press RYY, that's rotating around the local Y-axis. Okay, so this is almost right. Not quite, but we're almost there. Okay, so once you got to this point, once again, select everything and apply all transforms. Now what we want to do is we want to rearrange, make sure this phosphate group here is in the right position so that it can bond all the way up the chain. And the way that we're going to do that is we're going to create a duplicate of the deoxyribose molecule, and we're going to put it in a position that we know is accurate for DNA. So the unit spacing here is between each nucleotide. Okay, so this repeats itself, each nucleotide. And this distance, if you look it up in literature, is about 0.34 nanometers or 3.4 angstroms. Now you might remember that we've actually set a scale for everything here. We did this in the script. If we scroll right back up to the top, we can see that the radii for all of the atoms have been set in picometers and then scaled to a point where they were, easily manageable in the standard scaling. So if we apply this same scaling to the nucleotide distance, everything will match up correctly. So 3.4 angstroms is 340 picometers. So if we take 340 and multiply it by 0.4 and divide it by 30, which is the scaling we applied here, that's 4.5. Okay, so let's duplicate this. And to do that, right click on it in the hierarchy, and then duplicate collection. We'll hide the original deoxyribose, and then we can, is this parented correctly? Yep. So now with the origin right in the center here, we can raise this by, what did I say? 4.5. Okay, and in a full rotation, in a 360-degree rotation in the helix in DNA, there are 10 nucleotides. Okay, so that means that with each nucleotide step, there's a rotation of 36 degrees. The rotation transform here currently is in quaternion notation, which is rather difficult to deal with. So I'm going to turn this into an X, Y, Z Euler, and when I select this option from the drop-down menu, it will automatically convert this into a quaternion to apply. Okay, so the Z rotation, 36. And now if I bring back the original, this is the relative position that the deoxyribose sugars will be in the chain when we're actually in the DNA. So we just need to manipulate the position of this phosphate so that it's within one bond distance of this oxygen. Okay, so let's do that. So let's select all of these, not this bond, don't need that, and parent them to that oxygen. And then we can set the origin to the geometry of that oxygen. And now we can rotate around Y and then around X. Okay, so again, Control A, apply all transforms, and now we just need to rotate this bond so that it's sitting in the right place. So we don't really need to end snap it in this case because we can rotate it around the phosphorus. So just set the origin to the center of the geometry of the phosphorus, and then let's just rotate this into position. Rx, Ry, a bit more in X. And there we go. So now if we repeat this structure over and over again, we know that all the bonds are in the right positions so that every single one will be bonded up. Okay? We don't need this deoxyribose here. It's important that when you applied all these rotations and these changes, they were all applied to this one because this is the one we're actually going to use. This was just a reference position. So we can now delete this one. So right click on it, you'll see here there's delete and there's delete hierarchy. Delete just deletes the collection and spits all of the objects in that collection out into the scene. If you say delete hierarchy, it deletes everything. Okie doke. Right. Let's just make sure all those transforms are correctly applied. Yep. Okay, that's fantastic. So that's now done. If we bring back the AT molecule, you can see that it bonds up in the right position. And indeed, if we bring the CG molecule, it also bonds in the right position. That's why we aligned all the nitrogen atoms earlier. Okay, so now we can relabel this by double clicking as deoxyribose left, because it's the one on the left hand side. And now we need to duplicate this, duplicate collection, and name it deoxyribose right for the right hand side. So hide the left one. And yep, we're still parented to that, that's great. So now we need to flip this one in X, and then flip it as well in Z. Okay, and so now this is the correct orientation for the opposite, for the second helix. Oh God, what's happening to my view? Okay, so we can see here, if I line these up, that this is almost exactly right. But we need to do some more of the positioning, just like we did before. And particularly, if I bring back our AT molecule, you can see this is actually bonded to this nitrogen on the hexagon here, which is in the exact opposite position of this one. But actually, it needs to be on the pentagon. And this is the thing about DNA. It's often depicted as two helices that are perfectly in exactly the same period. Or rather 180 degrees out. They're not actually. They're out of phase with each other, and that's because of these different bonding sites. And that's why, if you look at the structure, you have this major groove on one side and the minor groove on the other side. It's because they're slightly offset from each other. Okay, so we're going to replicate that now. So hide the AT molecule, and once again we need to end snap to this point. Okay, so select everything, Control A, all transforms, tab to go into the mesh, Shift S. Ooh, that's because I've got something else selected somewhere. Shift S, cursor to selected, there we go. Right click, set origin to 3D cursor, done. Bring back the AT molecule. We now want this molecule, this nitrogen atom. So again, set origin to geometry. Now we have the geometric information back. Copy and paste this into here. Done. Okay. And now the procedure is exactly the same as before. We're going to replicate this collection, after I apply the transforms, of course. We're going to replicate this collection, and this time we're going to move it down by -4.4 and rotate it by -36 degrees, and then we're going to try and line up these bonds. I might fast forward through this because the procedure is exactly the same as last time, and you probably don't want to watch through the entire thing all over again. So here we go. Okay, I'm pretty happy with that. So let's just put the whole thing together. Yeah, bonds are in the right place. And if we look at the whole thing from above and we compare it to our reference, that looks pretty accurate. Maybe some of the phosphorus oxygen bond, the phosphate group is slightly the wrong angle. We can always fix that later, but we know it will join together. And this is the thing. If you want to have a perfectly accurate model of DNA, then you need to load it in from a reference model. But with this one, you'll be able to piece everything together yourself, including putting the groups exactly where you want them. So because of that, we're accommodating a little bit of scientific inaccuracy in the exact placement of the phosphate groups. Right. So now we have all the components that we need. It's just time to actually build our helix. So you're going to build this around a cube. So deactivate everything so it's not rendering. Shift A and then create a cube. Press full stop on the numpad to zoom in. This will appear on the 3D cursor unless you specify otherwise. So while we're at it, we can actually move the cursor back to the world origin with Shift S. And then set this position to 0, 0, 0. Okay, the reason we're creating a cube here is because of the what we're using are the normals. So if you go to this menu at the top right, you can get various information displayed onto different meshes. And if we press tab, so we actually go into the mesh view, and we go to this drop-down menu here, the viewport overlays, we can make the normal direction stick out from each vertex point like this. Okay, so what we're going to do here is we're going to make this into a 2D object, and we're going to turn it into a spiral, and we're going to use these normals to orient the molecules in our chain so that they inherit the right rotation. And unfortunately, we can't really do that with lines or anything else because they won't have this specific face arrangement that allows us to use these normals. Okay, so at the top left here, click on vertex select, and then just select all 4 top vertices, press X and delete them. Then do the same for the back 2 vertices, delete them. Now you see you've got a line with 2 normals sticking out exactly as they were before. That's what we need. You can just select those, and then you see here in the median transform, X and Z are at -1. Just put those to 0, so it's in the middle. Now right click and press subdivide, and that will put a point right in the center. Okay, that's that. Now we've got a line with 3 points, and we have normals that are sticking out according to the face orientation, which is exactly what we want. Now we're going to turn this into a spiral. So go on the right here with this cube, in inverted commas, selected, and go to the spanner modifier, which is the spanner menu, which is the modifier menu, and go down to where it says screw. Now what this will do is it will extend the mesh as a spiral in a particular axis, X, Y, or Z. Okay, so we need to fill this in to create our DNA. Now, as I mentioned before, a full pitch of DNA has approximately, or we're assuming, it has 10 nucleotides in it. Now, so the logical thing to do would be to make this exactly one pitch and then have 10 points. But we actually want to have 12. And the reason is that the normal positions at the top and bottom of this 3D object are going to be slightly skewed, which we don't want, because that will mean that at the top and bottom our nucleotides will be at an angle to everything else. So we want to have one like dead point at the base and at the top that we're not actually going to use. So here, this determines how many actual vertices this screw creates. So put 12, not 213, 12 into both, like that. We want it to go up in Z, that's fine. And we only want one iteration so far. You can, of course, do more than that if you want to have a much longer strand of DNA. But for now, we're just going to have one. And the screw, that's the actual length in the axis. So if we have a separation of 4.5 and we have 12 points, then in total we're going to want that to be 54.4. Okay, so let's put that in. There we go. So now you can see that we've got this double helix, this ribbon-like helix. Okay, now the angle here, you've got to bear in mind that the point at the bottom is like an anchor point, so that's at 0 degrees. So we have 11 rotation steps, and that means that we'll have 11 times 36 degrees, so we'll actually have a rotation of 396 degrees. Okay, right, so this should now be accurate for our double helix. Okay, so to turn this into an actual mesh, we click this down arrow and hit apply. So if I press tab now, you can see that all of the mesh points have now actually been generated for this spiral. And if we do have the normals displayed, so just very short. So if we zoom in, we can see that we have the normals that we want. They're pointing, well, normal to the surface of this ribbon. And therefore, if we use this normal as a reference point and get the objects that we're going to attach to them to inherit this rotation, we won't have to apply individual rotations to every object. Okay, so this dramatically simplifies everything. Okay, so what we're going to do now is attach the deoxyribose to this and check that they form the correct structure. Now we're not going to attach molecules to all three of these points, we're only going to use the center points. The side vertices are only there to ensure that the normals inherit the right geometry. They have no purpose other than that. So hold down Alt and click between two of the center vertices, and you'll select a vertical line of them. Okay, now shift click at the bottom and the top to deselect those points. And with it in this configuration, go to this triangular green shape here, which is the vertex groups, and create a new vertex group. Call it Deoxyribose and click Assign. So this is now an array of points in this mesh that contains these points. So we can now apply modifiers specifically to these points in the mesh, and that's what we're going to do next. So press Tab to go back into Object View and go to this branching thing here, which is the particle modifier set, and create a new particle instance, which will be called particle settings. We can rename this Deoxyribose, and for some reason you have to name it twice. Don't know why, you just do. And we want this to be a hair type particle instance. This is using exactly the same method as back in the very first tutorial I did last year on a simple cubic cell. We can use the hair modifier to create periodic structures. But we don't actually want this to be hair. We're going to use 10 actual instances, but for some reason this only works if it's 11. Something to do with how the arrays are set up. I don't really understand why. And the hair length you want to be 1. This corresponds to 1-to-1 scaling, and click Advanced. This will give us access to rotational properties. And where it says Source, open this drop-down menu and change Faces to Vertices and untick Random Order. Now going down, tick Rotation, and from this drop-down menu, select Normal. And then this is the important part. In Render, change it from Path to Collection, tick Whole Collection, set the scale to 1, and now drag and drop the Deoxyribose L collection into that spot. And there we go. That is sort of working. There's a gap here, and that gap is because we haven't applied the vertex group yet. So at the bottom here it says vertex groups, and you can apply all sorts of different things to different vertex groups. We want this to determine the density. So basically, within the vertex group, density is 1, outside the vertex group, density is 0. So select deoxyribose, and there we go. A chain of deoxyribose sugars. Now this happened last time as well, and I can't quite figure it out. For some reason, the rotation doesn't perfectly translate from our mesh to this particle instance. This has happened to me several times. One time it worked, and the other times it hasn't, and I'm not quite sure why. Okay. All the transforms have actually been applied. So what I'm going to do here is I'm going to rotate this. So I've reopened this collection and brought the cube back into visualization. And now if I rotate this bond, it will translate into all of these instances, so I can just fix it on the fly. So let's select that, Control P, set that to the parent, and let's just rotate it until it fixes. Ooh, set origin to geometry, forgot about that. Is that better? Yeah, that's better. Okay. Control A, apply all transforms. There we go. Okay, so yeah, there are always ways of fixing things if it comes out wrong. But there we go. There's our first chain of deoxyribose. So going back to the cube, add another particle instance, which we can call deoxyribose 2. And from the drop-down menu, select the deoxyribose particle settings. And on here, on the right, you'll see that there's a 2. This tells you that there are 2 linked instances of this particular property. Okay, so we've used it in both this particle instance and this one. If we click on that, it will separate them, and it will make them into 2 separate instances with unique properties. Okay. So now we need to just change a couple of things. We need to go down to the vertex group and assign deoxyribose. For some reason that never carries over when you duplicate. I don't exactly know why. And now we need to swap deoxyribose L for deoxyribose R. And there we go, now we have the opposite side. And again, for some reason, the bond is not quite perfect, but again, we can fix that relatively quickly in exactly the same way. Doesn't matter really that much unless you're a perfectionist, which I sort of am, I suppose. Right, apply all transforms, Control A, apply all transforms, there we go. And hide that again. There we go, fixed. And it's worth checking that there's no additional phase coming in, so as you go up the chain, the bonds aren't moving position, but this all looks good. Now, what you can see, if we click this and we go into an orthographic view, there you can see we have the major groove and the minor groove, exactly as we're supposed to. Okay, and that indicates that we have got all the structural parameters correct. Okay, so now we actually need to add the base pairs. So for this, what you can do is you can just pick out points and create a vertex group for AT and CG pairs. Okay, so let's say we want AT here, 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 and here. Okay, that'll do for now. Go to the green triangle, create a new vertex group and call it AT, and click Assign. And now, if we press Tab to go back to Object View and go back to the particle settings, we can add another particle instance, call it AT, once again, select Deoxyribose from the drop-down menu and separate it to create a new type. This just makes sure that all of these fiddly parameters, we don't have to do this every time, because the only things we're changing are the instance collection and the vertex group. So select AT from the vertex group and then drag and drop AT into the instance collection. And there we go. Now we have those AT groups appearing where we want them. And because we aligned everything correctly, you can see that all the bonds here, they all line up. Okay, and now we want every gap that doesn't have an AT in it to have a, sorry, slightly panicked, so I wasn't actually recording, but I am. Now we want the CGs everywhere else. Okay, so select the cube, press tab. Okay, now if we go to the vertex groups, go back to the deoxyribose one, click off first, sorry, deselect everything, then go back to the deoxyribose group and click select. So this now selects all the points that are in that deoxyribose group, which is all the active points. Then click on AT and deselect. That deselects all the points associated with this vertex group. So now the points we have selected are all the ones that don't have an AT pair on. Now create a new vertex group, call it CG, and hit assign. And now, just as before, go back to the particle menu, and one final time create a new particle instance, call it CG, select Deoxyribose from the drop-down menu, go to the vertex group, insert CG, and then drag and drop CG into the instance collection. Ugh. What's happened? Ah, there we go. I forgot to click here to separate these out, so I've just modified the behavior of both this and this at the same time, which was not my intention. So let's just fix that, change that back to deoxyribose and drag, I think it's deoxyribose L, yes, into there. Separate them, I can rename this CG. And now we can change it. There we go. And now we have cytosine guanine groups or adenine thymine groups in each slot with exactly lined up deoxyribose chains. And all the geometry here is exactly correct. The spacing is correct, the orientations are correct. The only thing that is slightly off, if you look at this from above, you will notice, if you're a crystallography nerd, that this is not right. These phosphates are not in the correct position. And this is basically because we had to slightly fudge their position in order to fit everything together in this way, but it is quite close to being correct. If I show you in my reference material, scroll down, okay, that's what it should look like, which is nice and regular, and this is just a tad chaotic in comparison. Okay, but it's close. If you really want to get really fussy with it, what you can do is you can add an offset to each vertex point to offset these a little bit in X, and then you can actually get the crystallography exactly perfectly right. But it's quite a small addition, and you'd only notice it really if you were looking right down from the top. Okay, so now we actually have our DNA. Done. Finished. Fantastic. But this isn't really renderable. It's a nice model, but it's not that useful for making a nice shiny magazine cover or something. So now what we need to do is make this into something we can actually render. First of all, we obviously have this ribbon in the middle that we don't want. Now, as I said before, the outer points actually have no value to the geometry except determining the normal direction. So what we can do here is in the X and Y dimensions, we can make this really small. We can't make it 0 because then the whole thing will collapse, but we can make it really small so that it's effectively invisible. There we go. So now you can't actually really see it at all, but it's still giving rise to the correct geometry. And we can go one further than that because we can select the cube and go to the material properties down here, and we can create a new material, and then in this printable BSDF material properties. The alpha here, take that all the way down to 0, and that will mean it is actually invisible to the renderer. Okie doke. So, a couple more things. We added these sort of matte colors to everything, so that you could just see what it looked like in the viewport, but maybe we want these to be a bit nicer looking rather than just kind of plastic ball and stick. So that's what I'm going to do now, but in order to see what these materials really look like, we need to set up the rendering scene properly. So first of all, go into viewport shading. You'll notice immediately everything is very grey and very dark. That's because we don't have any light sources in the scene. So press Shift A, scroll down to light, and create a sun, which is by default created at the world origin, and just tilt this ray to determine the sun direction so that it's nicely illuminating the model. Now, this is currently operating in Eevee, which is why it looks kind of weird and cartoony. So if we go to render properties on the right here, clicking the camera, we can put this into cycles and then use the GPU to render it, which should be a lot better. It still looks really matte and plasticky, but this is now a problem of the materials rather than the rendering. So now we need to sort out the materials. First of all, I'm just going to turn on denoising. Again, as I said in my first tutorial, do just be a bit careful when you switch into GPU computing for the first time and when you add rendering, because sometimes it can take a really long time to load and then your computer can hang. So just do be aware of that. Speaking of, I'm getting a bit of coil whine off my... Yeah, I'm really getting some coil whine off my GPU. Maybe you can hear it, I don't know. That's not good. Anyway, it will be fine for now, I'm sure. Okay, so these materials look really plasticky. So what I'm going to do is I'm going to bring back the AT molecule first. Let's zoom in on this, and we're going to edit these materials to make them look nicer. So let's go to the materials. And what you'll have noticed, I'm not exactly sure when this happens. Sometimes it happens, sometimes it doesn't. When you're duplicating these collections, sometimes it duplicates the materials as well, which isn't very helpful. Now it might be kind of difficult to figure out where, you know, having to go through and change all these materials manually. So there's a useful thing you can do. If you have something selected, you can go to the select menu and you can select things that are linked to it by certain properties. So for example, if something's in the same particle system as something else, you can select all of those. If it's in the same collection, or you can select everything that shares the same material. And there we go, we've now selected all the hydrogen atoms in this molecule. And now if we go here, use nodes, that will set up a printable BSDF, and we want these to look nice and metallic, which they should do already, but as I say, for some reason it lost a lot of the information. Okay, quite happy with that. Right, carbon the same. So select linked by material. Okay, all of these carbons are the same material, that's fine. You don't need to select all of the carbons. It's purely the case that you want to check that all of the carbons in this actually have the same material assigned to them if your materials have been duplicating in some strange way. Let's make this a little bit more metallic, bring the roughness down. That looks pretty good. Oxygen. Okay. There's only 2 here, so I'm not too worried about it. That looks good. And then nitrogen. Okay. Now I got a really nice look to these in my original test. I'm going to see if I can get it just by making the blue a little bit lighter and then adding a different subsurface to it. Let's see if I can recover that. I went over some of this in my original tutorial. Looks good enough. Okay, so if we look up at our full structure now, you can see that wherever the AT groups are, we now have nice fancy materials. But the other ones, even though they're supposed to share materials, they haven't actually inherited them because of this weird duplication process. Okay, so now I'm going to hide this one, bring back the CG, and then I'm just going to quickly do the same here, which I will fast forward so you don't have to sit through the whole thing. Okay, there we go. So now all those materials have been updated and it looks a little bit better. So now we actually need to make this render nicely. So the first thing is we only have one pitch here, and ideally we want to have a strand of DNA that we can have going off into the distance. So to achieve that, what you want to do is select your cube, and then we need to add a new modifier to it called an array. And we use this pretty much whenever we're trying to create periodic structures. So this just repeats the mesh for a particular number of times with an offset in a particular direction. So with the relative offset ticked, we want to put 1 in the Z column. That means it will replicate itself 1 step in the Z direction. And let's say we want 4 counts. Now, if we actually show, I need to expand the cube again. So press S, Shift Z, and I can expand it to show you. Oh, I might just have to edit it in here. There we go. Right, so you can see now that that ribbon is going off into the distance. Although, one thing I just realized, of course, because we have more than one full rotation, these ends won't completely match up. So actually the Z offset needs to be 0.9, and then this will match up perfectly. Okay, so now if I take this drop-down menu and I click apply, it will turn this into an actual mesh. Okay, so now we have our nice long strand of DNA, but you can see that all these molecules are now all in the wrong places and there's loads missing. That's because we set how many particles we wanted in each of these particle instances, so it's only rendering that number of instances, so it's not covering the whole thing. So let's put this back down so we can't see it. Okay, and if I go to the particle instances now, and we just, how many steps did I have? 5? So I just multiply each one by 5 in the number. We'll get enough molecules to fill the whole thing. And there we go, there's our strand of DNA. Okay, so the final thing which I want to do is show you how to composite a rendered image to make it look really nice. Because while this is a nice model, it's just against this dull grey background, and if we rendered this, it wouldn't look great. Okay, so there's a couple of additional things that I want to do. In order to render anything, we have to have a camera in the scene. So press Shift A and put a camera in. Press 0 on the numpad to go to the camera's view. Go to View in the N menu and select Camera to View. And now as you move your view around, the camera will follow you. So let's find an interesting perspective to look at this strand of DNA. Ideally one where we get the large and small groove and we can see. There we go. That looks much better. Okay, so now we have a camera in the scene. And what I want to do, we want to add a background to this that's not just grey. So to do this, you need to go to the scene settings, go to the film drop-down menu and make that transparent. And now when it renders it, this will all just be alpha. Okay, now press F12 to do a test render. There we go, there's our strand of DNA rendered. And now to actually turn this into a composited image, you want to go into the Compositing tab and click this bit that says use nodes. Now it's taken that image that we've rendered and we can now manipulate this. Okay, now to view the end result, this is nodes just like in the shader nodes. Okay, they're working the same way, but this is handling images rather than handling textures. Okay, so we have this image that we've produced, and that output is going into this compositor, which will give us our final product. But we need to view what we're doing. So to do that, press Shift A and go to Output and put in a viewer. That's interesting. I'm not getting my screen. Oh, I am. There we are. Screencast keys are down there. Okay, so now if I drag this image node to here, I can see what I'm actually creating in the background here. Now what I want to do is I want to, in this alpha region, have a background image that's layered in with my DNA on top. Okay, and the one that I want, if I go into my DNA tutorial folder, is a nice blue. Oop, why is that not loaded in? There we go. So it's this nice blue background. This is a free background image that I found on Google. Obviously, feel free to use your own, whatever you think works. And now we just need to put these two images together so that we fill this alpha space with this image. So to do this, press Shift A and go to Color, and you want to use this alpha over filter. So what this means is that we put in two images, and wherever this image has the value of alpha, it puts in this image instead, the top image. So if we drag that into there, and that into there, get rid of these two, just drag them off into free space and let go, and then take this output into the compositor and into the viewer, and there we go. Now we have the DNA floating against this nice bioscience looking background. But one of the things that will happen if you try to render this now, if we press F12, is that this doesn't actually fill the full image, and that's because the rendered image and the background image are at different resolutions. So the way we can change this is by, from the Shift A menu, putting in scale into here and clicking render size from the drop down, and that will scale it up to fill the render window. And now if we render it, there we go, now it fills the full space. Okay, there's a lot of other things you can do with compositing, but this video is already quite long, so maybe next year I'll get round to showing you some of the more interesting things that you can do with compositing. But for now, here is your model of DNA, which you can fully customize, change the materials, change the sizes of the atoms, whatever you need. But this is geometrically accurate and chemically accurate, and I hope it's useful to you, and I hope you learned something from building it over such a long period of time. Thanks very much.